Hello. Continuing on with proof by induction, we are looking at divisibility proofs today. And again, our proof by induction follows our 4 steps, and it always follows those 4 steps. The first 2 and a bit get us 50% of the marks in the exam, and that's definitively what everyone is going to get. And then we're going to look at the extra steps beyond that. The reason I'm focusing on that is that we're about to see that a proof by induction requires us to remember lots of special little rules. So we saw the series rules already, and divisibility is going to work a little bit differently. So because it's finicky, that's why I'm focusing on the first steps that get us the bulk of the marks that are very easy to get. Now, we're going to follow these steps for proving that 6 to the power of n minus 1 is always divisible by 5 for any value of n. For any value of n that is a natural number, I should say. So, what's step 1? It's going to be proved that this is true for n is equal to 1. And again, we know that sometimes you might say n must be 2 or 3 or greater than a particular number. But in this case, we can just say n is equal to 1. So set n equal to 1, and we get 6 to the power of 1 minus 1 is equal to 5. 5 is indeed divisible by 5. If I have 5 divided by 5, I get 1. And divisibility is going to mean that effectively 5 is always a factor of this. If I have, I'll write down the situation in the abstract for my second stage, n is equal to k. So that's going to be, I'm going to assume that 6 to the power of k minus 1 can be divided by 5, and give me a number, we'll call it m, where m is an element, I should say, of z. So this is divisibility, or showing that 5 is a factor of another number, which means that if we divide this by 5, we get a whole number out. That's what we want to prove when we are looking for a divisibility type proof. And it will be very straightforward in the exam. There won't be a pile of English. It will literally say this line here, prove this is divisible by 5. That's what the questions look like. So there's no hidden bits in a proof by induction. They're complicated enough already. They just tell you exactly what they want. Now, this is our stage 2, and I've stated that I'm going to assume that this is true, and then I'm going to go to stage 3. Now, stage 3 is a little bit different than it was for the series proof. My aim is still identical. If n is equal to k is true, then n is equal to k plus 1 must also be true. That's still going to be my aim. If n is equal to k is true, therefore n is equal to k plus 1 must also be true. But before we started with the series problems, we started with n is equal to k, and we modified it to show that if n is equal to k was true, therefore n is equal to k plus 1 must also be true. We started with n equals k, what we'd assumed. This time, we are going to start with n is equal to k plus 1 and use substitution. I'm going to find, or I'm going to rearrange my n is equal to k plus 1 to show that part of it is the same as n is equal to k. Now we're going to look at exactly how we do that right now. So what does n equals k plus 1 look like? Well, it just means that I'm going to have a k plus 1 anywhere that I had n. So that's going to be 6 to the power of k plus 1 minus 1. And I want to show that this must be divisible by 5. Now, if I have powers added, that means that I used to have base numbers multiplied. This is one of my indice rules. I must know them very well because they come up in several different parts of the course. So if I have my powers added here, this means that I originally had 6 to the power of 1 multiplied by 6 to the power of k. And I remember that a dot can mean my multiply. You could also put these in brackets, which is, I think, actually what I will do here, but the dot is good to remember. Now, here's effectively the trick we have to remember, or for this type of proof, for the divisibility type of proof. I am going to break up this 6 to the power of 1 into 1 plus 5. We know that 1 plus 5 is 6. But what we need to recognize is that we want to break this up into stuff that is divisible by 5. Now, what does this give me? It gives me 6 to the power of k plus 5 6 to the power of k minus 1. What do I recognize? That and that is the situation I had for n is equal to k. That's the n equal to a kth situation. So I'm going to rearrange that. So I have 5 multiplied by 6 to the power of k plus 6 to the power of k minus 1. I have assumed that this bit is divisible by 5, and something multiplied by 5 is obviously divisible by 5. So this is essentially my work done. This breaking up of my 6 here into 1 plus 5 into something that's going to give me my n equal k position and something that's divisible by 5 is the trick to divisibility proofs. Now, under exam pressure, we might not remember that, but what we do remember is that down to this line here, if I write the n equal k plus 1 situation, if I write down to this point here, so this part of the question, I have 50% of my marks. I'm guaranteed I'm going to do that. And then if I can remember the factorizing or breaking up my 6, I can build towards the rest of the marks. But I'm definitely getting those first 50% of the marks. Now, that is my part 3. And I need to have a final statement as normal for proof by induction. So I'm going to write my part 4 now. As n equals k plus 1 is true if n is equal to k is true, and I have shown that n is equal to 1 is true. Therefore, this relationship will hold for or n is equal to 2, which would be the k plus 1th situation. Therefore, if it's true for 2, it must be true for n is equal to 3, and so on. Therefore, I have shown that this is true for all values of n. This is the final block of marks. This little sentence here is 4 marks out of 15 or more if it's a higher mark question. So this is not an optional extra. These 1, 2, 3, 4 steps are in the marking scheme. They're what's required. So there is no change in the way that you write these type of questions. You must do them always the same way. Now, I'm going to look at another question quickly here. I want to show that 7 to the power of n minus 2 to the power of n is divisible by 5. This is going to follow basically the same steps, but I'm just going to show it to you because I know how strange these questions come off as, and I want to highlight to you how easy it is to pick up the first block of marks, because that's really what I need everyone to understand. Even though this is a very alien style of maths, the block of marks that we can pick up very straightforwardly for this type of question should not be ignored. So I'm setting n is equal to 1. That's my first step in all of these questions. That's equal to 5, and 5 is definitely divisible by 5. Gives us 1. Same situation as we had last time. There is no significance to the fact that both of these are divisible by 5. It just happened to be when I was coming up with questions that I ended up with dividing by 5 both times. So it could be divisible by 4, divisible by 3. It doesn't matter. You'll be given that context in the question, and you just work with the context that you're given. Now, part 2, n is equal to k. We're going to assume that that is true. So what is that going to look like? We're going to assume that 7 to the power of k minus 2 to the power of k is definitely divisible by 5. So it's going to be equal to m where m is an element of z. That's what we're assuming to be true. Now I'm going to, if n is equal to k is true, again, I sometimes use tick for true because it's faster to write, but true is a better thing to write in general. If n is equal to k is true, then n is equal to k plus 1 is also true. Steps are identical each time, but we know for a divisibility proof we're going to start with the n equals k plus 1 position and see if we can use the n equals k position to help us along the way. So that is what the n equals k plus 1 position looks like. I now have 50% of my marks. And I'm going to continue on trying to factorize this. That should have been a plus. And I want to show that this must be divisible by 5. And I'm going to use my n equals kth position and my factorizing or breaking up to solve the problem. So I'm going to have 7 multiplied by 7 to the power of k. Why? Because I have 7 to the power of k plus 1. I'm adding my powers. That means my base numbers were multiplied. This is 7 to the power of 1 multiplied by 7 to the power of k. I know that that is 7 to the power of k plus 1. Minus 2 on 2 to the power of k, identical argument there. Now I need to get clever with how it is I can factorize this or break up my 2 and my 7 in order to end up with something that's going to be divisible by 5. So I can't break up my 2 into anything that's obviously divisible by 5, but I know that I can break up 7 into 2 plus 5. And really these questions are just getting used to how you can cleverly break up the information you're given into something that's going to be of use to you. And it's simply a matter of getting used to that skill in the different contexts for the different styles of proof. So I now have this broken up, and I have 2 multiplied by 7 to the power of k plus 5 multiplied by 7 to the power of k minus 2 on 2 to the power of k. I didn't need to put that in brackets, but anyway. So now I recognize that if I take my first term and my last term, and I take out a common factor of 2, I will have my kth position, which I've assumed is divisible by k. So I'm going to have 2 on 7 to the power of k minus 2 to the power of k. That's just taking the common factor of 2 out of these two terms, and I still have plus 5 multiplied by 7 to the power of k. This I have assumed is divisible by 5 in step 2. This is multiplied by 5, so therefore this is automatically divisible by 5. Therefore I'm writing out my last few steps. So finalizing then, we're just writing basically the same thing as we usually do at the bottom of our proof by induction. As we have shown that the k plus 1 position is true if the k n is equal to k position is true. So our proof that n is equal to k plus 1 works out, that it's divisible by 5, only holds if our n is equal to kth position, our assumed position, is true. That's the first part that we've written here. So n is equal to k plus 1 is only divisible if we are assuming that n is equal to k is divisible. So if that's true, and we've shown that n is equal to 1 works, therefore the next value of n must work, and so on up for all values of n. So you can see that there's a definite overlap in the styles of our proof by induction, but in the case of divisibility, we start with our n is equal to k plus 1 position, and then use the n equal k position effectively as a kind of a substitution at the end to prove our situation. So that's what we have for the first types of divisibility proof by induction.